Right, let's have a short prayer as we start. Father, we thank you this evening. Bless you for bringing us together once again. As we go through this class, we pray for your guidance. In Jesus' name I pray, amen. All right, so we are looking at these examples. And the first one says that the cylindrical rod in a machine assembly is subjected to a tensile load of 4.9 kilonewtons under rough service conditions. And we are to design the rod. Okay. This question, I would say that it's not complete. Looking at it, to be able to size a component or to design a machine part, we need some information on the material used for the part. By this case, we know nothing about the material. We only have the loading condition. And therefore, without the material, we cannot design this. Are we following? So,
Yes, sure.
yeah, so unless we decide to, let's say, assume a material. And if we are assuming a material, we need to be able to determine the ultimate stress in the material and then decide on the factor of safety that we are using for the design. In that case, we can say that the stress buildup in the material or in the parts or elements should not exceed the allowable stress in the material. And here, this is tensile loading. So with this tensile loading, we know how it's loaded. We have axial forces. Okay, so in effect, we are going to have a direct stress in the material or tensile stress in the material. And if we know the allowable tensile stress or the ultimate tensile stress in the material, we can, based on the factor of safety that we decide to use or based on where this part is going to be used, we can decide on the factor of safety to use. Then if you know the factor of safety and we also know the ultimate stress in the material, we can determine the allowable stress. And the allowable stress here is basically the stress or the ultimate stress in the material divided by the factor of safety. Then we have the allowable stress. Now, what we'll say is that the stress buildup in this material should not exceed the allowable stress, okay? And we know the equation to determine the tensile stress in the material is basically equal to the force that the material or the object is subjected to divided by the cross-sectional area, okay? And the cross-sectional area in this case is, this one is a cylinder, a cylindrical rod. So cross-sectional area is basically the area of the cross-section of the rod, which is finding the area of the circle. And in that case, the only unknown there will be the diameter of the rod, okay? So we are going to have the allowable stress because we don't want the ultimate stress to exceed the stress in the material should not exceed the allowable stress. So we can say that for this design to be satisfactory, it means that the ultimate the stress in the material based on the loading should not exceed the allowable stress. So we can say that the allowable stress is equal to the stress in the material. So in this case, the allowable stress is equal to the stress in the material, which is F, the force applied, divided by the cross-section area. The allowable stress, we know it based on the factor of safety we are using. And then we also know it based on the factor of safety and the ultimate stress in the material. So in that case, the only unknown in that equation will be the diameter of the rod. So make the diameter of the rod the subject and you solve it and you will have the diameter of the rod. And in that case, you have designed it. I hope you're okay.
No, sir.
Is that what? Hello?
Hi.
So let me open my sketch book so that we can look at it briefly. Hello?
Hello. Yeah.
Can we see the screen?
Yes, sir.
Okay. Yeah.
Okay. So in that particular case, we have what do we have? We have an assembly, okay? A cylindrical rod in a machine assembly is subjected to tensile load of this amount. And we are to determine the designing of the rod is basically determine the diameter of the rod. Okay. So if you have tensile load in this case, it means that we are not looking at the length of the rod. It's tensile loading. So we just design based on the loading in the rod, which will affect the cross section of the material or the cross section of the part. Okay. So let's look at it. So the load given in the material is a tensile load of 4.9 kilonewtons. So let's say that the force F is equal to 4.9 kilonewtons. I hope you can see my writings. And
Yes,
we have this rod. So let's say that the rod is like this. Let's say we have it like that. Okay, so we are just showing a section of the rod. Okay. And this rod is subjected to tensile loading. So we have the load along the axis to be F and F. And this F is 4.9 kilonewtons. We had to design this rod. And we were told that this rod is subjected to this load and is under rough conditions. Let me take a snip of the question so that I'll paste it on the board.
Please, what do they mean by it is subjected to rough conditions or that segment? Can you explain better?
Yeah, I will look at that. We'll look at it. So let's take this the question. And we have to design it. So what I was saying is that the information we have about this question is not enough. To be able to design it, we need the material that is used for the rod, okay? And in this case, we don't know the material. It wasn't given to us. We only know the loading and then the condition that which this part is to operate. So we need to determine the loading in the material, okay? And to determine the loading, we can do it by we know the loading. So to determine the material, this we're not giving the material, so we have to assume the material for purpose. Okay, so let's say that the ultimate stress in the material, okay, let's say it's a mass steel material. The ultimate stress is equal to, say, 60 megapascals. So if we assume that the ultimate stress, say, sigma ultimate, okay, is equal to, say, 60 megapascals. So in this case, we need to determine the allowable stress. We mentioned when we're defining the failure modes in materials that materials usually design is done to operate lower than the ultimate stress or the failure stress in the material, okay? And that gives room for some safe margin so that if it should fail, or if there are loads which are applied to the material is more than, or those loads are more than the design stress in the material, we have a safe margin that the material will not fail. So in this case, if we say that the ultimate stress in the material is 60 megapascals, we don't design with the ultimate stress. We need to design with the design stress or the allowable stress. And the allowable sigma allowable is equal to the ultimate stress, which is sigma ultimate divided by the factor of safety in the material. So factor of safety, let me call it SF in the material, okay? And the SF in the material, we can decide for the factor of safety based on the usage condition of that particular part, okay? So that is where this, that is where this rough condition comes in. This under rough condition, that is where it comes in, okay? So if the Hello. Hello. Are you here?
Sorry, sir.
Okay, thank you.
Yeah, yeah.
So then we'll ask what should be the appropriate factor of safety for the design. And the appropriate factor of safety for the design, we have it in the table when we're defining the factor of safeties, and then the appropriate values to be used for it based on the condition, the service condition of the part. So let me share that screen too for the factor of safety. So here we have the table. Okay, we have factor of safety and the application. So when talk about the rough condition, it's for specific service conditions, example, rough service conditions or unusual conditions. Okay, and in that case, we can decide on the factor of safety to be between or from 4 to 6.0, 4.0 to 6.0 as the factor of safety. Okay, so let's say that for these rough conditions that have been defined in the equation, let's say that the factor of safety is 4. So if it is 4, then we can use the 4 as the factor of safety in this case. So we have picked a value for the value for the ultimate stress. So the allowable stress will now be equal to 60 divided by 4, assuming we take our SF to be equal to 4.0. And this will give us what? What will be the answer? So we have 60 divided by 4 is what?
15.
15. So we have 15 megapascals as the allowable stress in the material. And what I was explaining earlier is that when we have this allowable stress, we need to be able to size the shaft based on this allowable stress. So we can say that the stress in the material, let's say sigma in the material, the sigma in the material should be less than or equal to the allowable, okay, to be less than or equal to the allowable stress in the material. Okay, so for satisfactory design, the stress in the material should not exceed the allowable stress. And if that is the case, we can say that then we can say that sigma, if we are to design this cell, we can say that then sigma is equal to the allowable stress. And what is sigma? That is the stress in the material, and the stress in the material is equal to the F divided by the cross-sectional area. This is a rod, so cross-sectional area for the rod is pi d square divided by what? 4. So we know A to be A is equal to pi d square on 4. F, we know the value of F to be 4.9 kilonewtons. So in that case, if we put A here, then we can say that our sigma is equal to 4F divided by pi d square. Now, if we are saying that sigma is equal to the allowable stress, then in effect, we are saying that the allowable stress which we have calculated, okay, the allowable stress which we have calculated to be 15 megapascals is equal to this expression here. Are we okay? Or let's say that we find the sigma to be equal to 4 times 4.9 times 10 to the 3 divided by the pi d square. If you calculate this, what do you get? In terms of d, so you are going to get some value over d square. What is it?
Uh, 6238.87 over d squared.
62 what?
6238.87.
So you are having
6238.87 over d squared.
62.87 over d square. Is that correct?
Yes, sir. Yes, sir.
Okay, so if that is the case, let's move this somewhere. So if that is the case, we have that value, which is 6238.87 on d square to be equal to the allowable shear stress, which is 15 times 10 exponent 6. So we can say that our D is 6238.87 divided by 15 times 10 exponent 6. So what is the value?
41592 blah 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 blah.
Is what? So let's find d square. Okay, so let's say that the D is equal to square root of all that. So D is the square root of all that expression. So find the D and let's see. What is D?
0.0203.
0.0203. That's in meters, right? Or we can say that it is 20.3 millimeters. Is that correct?
So make it 20.4. Is 0.0204.
Okay. 0.0204. Okay, so here should be 20.4. Okay, so that is this should be the diameter. So to be able to determine the diameter for this, we need to first of all have the material, or the material properties. Okay, the tensile stress in the material, and then based on that, and then the factor of safety that we select, we can determine the allowable shear stress, allowable tensile stress. Then from there, we can size the material as given. Any question? Yes.
Sir, please. So The question said we should design the rod. So does that mean that you are going to find the diameter just as we have done?
That's
So
the
after finding the
design.
diameter,
Yes.
after finding the diameter, are you going to draw or just leave it like that?
Draw, you don't need to draw. You can sketch like I've sketched as we are doing the calculation, but you don't need to draw anything.
Okay, sir. So if I understand it correctly, it means that the main thing I'm finding here is the diameter of what?
Yes. So that
Cylindrical.
is what it means. Design the rod. Determine the diameter of the rod.
Thank you.
Are you okay?
Yes, sir.
You are good, eh? Okay,
Yes,
then
sir.
there is another one. That one says that have a nozzle, okay? It's a nozzle. And that nozzle is subjected to some loading. So again, that one too is not complete. If you look at it, it says that, let me share that one too. Yeah, it says that shown in the diagram is the principal sketch of a pulley rotating on a fixed axle. Determine the diameter of the axle. Given, so we have the force exerted on the axle by pulley. F is equal to 4.9 kilonewtons. Force acting in the middle of the axle. And then there we have the load, L. Then under rough service condition. So if it is under rough service condition, how do we go about it? There is another one. I think the actual question should, excuse me, I'm coming. Okay, so it says that an axle 1 meter long, supported in bearings at each end, carries a flywheel weighing 30 kilonewtons at the center. If the bending stress is not to exceed 60 megapascals, find the diameter of the axle. So in this case, we have some force in the middle. So let's take the force we have here, 4.9 kilonewtons. That is the force exerted on the pulley. And that force is at the center of the axle. So if it is at the center of the axle, first what you need to do is to determine the bending moment in this arrangement. Then if we know the bending moment, we can determine the bending stress. And again, we equate the bending stress to the allowable bending stress given to us. Are we okay? So it's similar to the other one. So here, we need to draw the free body diagram, indicate the loading, then we can determine the bending moment. And then when we have the bending moment, we can determine the bending stress. And the bending stress is based on the moment of inertia, okay, of the section. And this is a cross section. It's having a cross section that is a circle. So that determining that will not be a big problem. Okay, so let's look at it. So first of all, we have the pulley and then the axle arrangement. We have pulley axle arrangement. Let's say that the axle is somewhere here, and there is the pulley at the center. Okay, so we have the bearing which is supporting the axle. And I hope you know what an axle is. There's a pulley in the middle of the axle. So here we are going to have point loads at this point. Then the weight on the load on the pulley, we act in the middle. And we're giving the force of that to be equal to 4.9 kilonewtons. And we have to determine the diameter of this axle. Okay. So let's say that the allowable stress in the material. So let me state the things given. So we have F. F is equal to, the force F is equal to 4.9 kilonewtons. Allowable stress in the material, sigma allowable, is equal to, say, 60 megapascals. And this member is having a length of, what's the length?
100 millimeters.
Is it 100?
Yes.
Okay, 100 millimeters, that's good. All right, so the length is 100 millimeters. Then this force is acting in the middle. Okay. The force acts in the middle of the axle, so it's acting in the middle, so halfway. So we can see that the distance between the force and then the bearings should be what? 50 millimeters. So what is the bending moment on this? What will be the bending moment? To determine the bending moment, first we need to determine the support reactions. Okay, so the reaction here, let's say this is R1. Because the load is acting in the middle, we are going to have, if this is R1, it will be equal to 4.9 on 2. Okay, and this will be 4.9 on 2 in kilonewtons. What will be the value? 4.9 divided by 2 is what? It's what?
2.45.
So we have 2.45 kilonewtons, and R2 will also be equal to 2.45 kilonewtons, because the load is acting in the middle, so the reactions will be shared equally. And we know that bending moment M will be equal to, in this case, if we take a section along that and want to find the bending moment, we know that it will be basically be equal to the reaction, one reaction, 2 point, or let me say, if we are taking section at this point, we'll find the bending moment, R1 times X. Okay, so that's the distance. So we can say that it's 2.45 times 10 to the exponent 3 times 0.05. And the answer will be what? What's the answer?
One to 2.5.
He said, where are we taking the moment from?
Is that
Which reference point are we taking the moment from?
we are finding bending moment? Okay,
R1.
bending moment at the center of the axle.
Okay, sir.
Are you okay?
Yes, sir.
Good. So in this case, you say you have what?
1 to 2.5.
1 to 2.5 Newton meters, okay? So that's the bending moment at the center. And if we have the bending moment at the center to be that, what will be the bending stress? Bending stress is equal to what? Sigma B is equal to my over I. Do you remember?
Yes, sir.
So the Y for, we need to find the I, we need to find the Y. Okay. So what is Y and what is I? What's the formula for Y? For a circular cross section.
Can we use the sectional modulus?
Is that,
The sectional modulus.
what's the formula?
Pi d cube on 32.
Pi d cube on what?
32.
32.
Yes, sir.
Pi d cube on 32. What is Y over I? Let's use this formula. Leave the section modulus. If you're adding the section modulus, pi d cube on 32, okay, which is basically Y over I, which is the section modulus. Okay, so if you want to use that to find the section modulus Z is equal to pi d cube on 32. But what is the moment of second moment of area for a circular cross section. That's what I want to know. Is what?
So pi of 8. So
Pi
1
on
on 4. 1 on 4 r exponent 4.
1 on 4.
Yes, sir.
Are you sure? Where are you getting that from?
Please say, is it 4r over 3 pi?
4r over 3 pi. Where is that from?
Yes.
Pi d4 64. Is that correct?
Yes, sir. Yes, sir.
Huh?
Yes, sir. It's correct.
You people, you have to revise your strength. So pi d exponent 4 over 64. But if we know we know y in this case to be equal to d on 2. Is that correct? So in that case, we can, if we are using the section modulus, that is where that value will come in, because it's like the section modulus. You are having y over I. And when you do that, you are going to have a 64 turning into what? 32. Then the d will remain 1d cubed in the denominator. Are you okay?
Yes, sir.
Okay, so with that understanding, let's use the section modulus, and that will be equal to 5d cubed on 32. So that this equation here becomes m divided by the section modulus. When we find this one, pi on 32 will give us what? What's the value for pi on 2?
0.098.
0.098. Okay, so it will be in terms of d exponent 3. So in that case, we can say that our bending stress sigma b is equal to the bending moment we have, 22.5 times 0.098. And when we compute this, when you compute this, what do you get?
$12.05.
12.05. Is that all?
03.
What?
12.03.
12.03.
Yes.
D cube. But this is what we are looking for. So
So
we know that sigma b should be equal to sigma b allowable, the allowable bending stress. Okay. Yeah, who said so? What's your question?
it's not m on z. By you wrote m times z.
Oh, sorry. So recompute it. M divided by z, that's the, it's m on z, not times. So we have it divided by 0.098 d cube.
1250.
125. What?
0.
Over D cube, right?
Yes.
Okay, so here, if we have the bending stress to be equal to the allowable bending stress, then we can say that 1250 over D cube is equal to the allowable bending stress. So let's say the allowable bending stress in the material is equal to 60 megapascals, okay? So if the allowable bending stress, sigma allowable is equal to 60 megapascal, then it means that this whole expression we have here should be equal to 60 times 10 exponent exponent 6. So we can say that D cube is equal to the 1250 divided by 60 times 10 exponent 6. So what will be the answer when you find the cubic root of this? So we can in effect say that D is equal to the cubic root of all that. So D is the cubic root of that one. What is the answer?
0.0275.
So we have D to be equal to 0.0275, and this will be in
meters.
meters, okay? Okay, so we have it in meters, and that is equal to 27.5 millimeters. Agreed? Are we okay?
Yes, sir.
Okay. All right, then I think our time is up, or we should go on. We should look at the last example.
No.
Oh, sir. We have a quiz
You have a quiz when?
right now. 6
Eh,
o'clock. Yes.
okay, so when should we wind up? You also need to have your last quiz. Oh. I think we'll do the quiz on Thursday. But we
Sir,
need
Sir,
to wind up everything before the quiz.
sir,
So
do it assignment. Do it.
no, you have to
Assignment.
write the quiz.
We beg. Oh,
The assignment will come. I'll send one assignment for you.
Assignment quiz.
Sir, we beg.
You need it for your continuous assessment. Now you only have one quiz, so we need to add another one.
Sir, multiply the first one.
Yes, sir, we'll do the
No, that is not allowed.
no, the quiz as answer. Oh, sorry, beg.
Okay, so I'm going to meet you again